All right, this is Tech 3421, and we're going to talk about mechanical properties today. So, as you already know, because you've had Tech 1711 and most likely you've had Tech 3401, the statics and strengths of materials class, you know that there are a lot of different ways to talk about strength. So we could be talking about tensile strength, we could be talking about shear strength, we could be talking about hardness or toughness. So a lot of these different ways of talking about strength, we need to sort these out because some of them or even conflict with each other. Like we talk about hardness and toughness. Usually when you have more of one, you lose some of the other. So we're going to back up just a little bit and talk about what we're, strength, and try to break this idea of strength down. So strength is the ability to resist the application of loads without failure. All right, so I guess what we have to do is figure out what are these loads, what types of loads we have, what types of responses we can have to those loads, and also, well, what constitutes failure. Okay, so if we look at this little hoist here, you might think of failure just being the whole thing crashing down, but it could be that if we turn this crank a little bit too much, apply too much force to it, that one of the teeth on this gear deforms plastically and gets bent enough that the thing doesn't function properly. All right, so it's not always a dramatic thing, this idea of failure, but so we're going to be designing, though, around some kind of a use. Okay, so if we're talking about failure, we're saying that it can no longer serve the purpose that it's intended to serve. All right, and hopefully you're thinking already of some of these types of loads. How could we apply a load, and how could the material respond? I've got a couple of slides, and we'll break that down a little bit more. But before we even start talking about this, is we need to think about this class being manufacturing processes. Okay, so on one hand, we are going to think about, how would you design a part using a particular material to serve a certain purpose. But on the other hand, what our idea here is that we're taking these materials, and in order to do any kind of manufacturing process to them, we need to be able to shape them or shear them. We need to be able to break them, and we need to be able to bend them to our will. We need to be able to get them into the shape that we need. So a lot of times, looking at these numbers like tensile strength from a manufacturing side, we're trying to make sure that we can overcome those strengths of materials. All right, so this is a lecture on mechanical properties, and mechanical properties are talking about how a material responds under applied loads. Okay, so this idea of mechanical properties deals with loads. We could talk about chemical properties, and in fact we will maybe a little later. How a material responds to certain environments and things like that, and certain chemicals. Thermal properties, how the material conducts or doesn't conduct heat. Also the same thing with electrical and magnetic, acoustical, and even optical properties. Okay, but for now we're going to talk about mechanical properties. All right, so this idea of a load, when we're applying a load, we're applying some kind of a force. Okay, and so it's good that you separate in your mind the difference between mass and force and weight. All right, so sometimes we'll get a load from a mass, but only if it's being accelerated somehow. Okay, so out in space, if we had a 2-kilogram weight, it could just float freely. But unless we tied it to a string and started swinging it around or threw it or something like that, then it would not be applying a force by itself. So mass requires some kind of acceleration, like gravity or other types of acceleration, to produce a force. On the other hand, we could have a force applied with very little mass. So we could have like a screw that's screwing down on an object, and it could apply a very high load. Okay, so the best way to think about this, I think, is by just thinking in terms of pounds force. Okay, so in this class and in every class that I teach, if we're talking about pounds, we're going to be talking about pounds force unless we have decided to break out and talk about pounds mass just to talk about pounds mass. Because you see, the unit pound is actually older than the distinction between force and mass, and so we can use it one way or the other. But in this class, we'll go ahead and talk about pounds as being a force. We'll already just have gravity multiplied in there, and so we don't have to worry about gravity. If we're talking about pounds, we're talking about pounds on planet Earth as they would feel. Another unit of load would be the Newton. And I think a good way to think about a Newton is to just think about an apple, all right? So something that weighs maybe about a quarter of a pound, or maybe you want to think of a quarter pounder burger patty or an apple. That's about how much a Newton would feel in your hand, anywhere, whether it was on planet Earth or anywhere else. Okay, so the amount of mass that it takes to produce a Newton would change on different planets, but it would still feel like a Newton. All right, so understand the difference between weight and pounds and mass. Okay, so if we were in the International Space Station and I threw a wrench at you, even though that wrench was weightless, it would have a certain amount of mass, and that mass would produce a force when it struck you. Okay, so a wrench could still do damage even in a weightless environment. You'd be applying an acceleration a different way. All right, so let's move on. I think you guys already, that's all review, so I'm not going to belabor that point. Now, we talked about in Tech 1711, usually I talk about this, that it's, let's see, so say you want to win some money at a bar, okay, and or say I'm trying to win some money off of you at a bar, and I tell you that I have a material that can support 60,000 pounds, would you be impressed? And of course, the answer is, well, it really depends. It depends on how big the cross-sectional area of that material is. Okay, so if I said I had a material that was 6 inches in cross-section and could support, or 6 inches in diameter, and it had a large cross-sectional area, then you wouldn't be very impressed the fact that it could hold 60,000 pounds. There are materials all around you that can hold 60,000 pounds. That's not really a big deal. Now, what would be a big deal is if I told you I had a material that was as thin as a hair and could support 60,000 pounds. Now, see, that would be really impressive and really incredible. And the difference is really stress. Okay, so this idea of stress is taking some force and dividing by a cross-sectional area. All right, so in this case, pounds, and we said already that these pounds are going to count as force, and divided by some cross-sectional area, that will give us a thing that's a lot more useful in certain circumstances than force, and that is stress. So the reason I'm using these U.S. customary units here, PSI, is because it will help you to sort out the idea of stress. If you just remember that PSI is a valid, although not super common anymore, unit of stress, then this pounds per square inch tells you the formula for stress. So if you just remember that PSI is a valid unit of stress, it tells you the formula, force per unit area, pounds over square inches. Pascals doesn't really just do that for you, okay, and we'll see that in just a minute. But anyway, that's how I like to keep it straight, okay. And so that's what we're seeing here. This is the cross-sectional area of this eye hook here. So if we had a force acting down to pull on this eye hook and put it into tension, the force is not going to be impressive. It's going to be the stress that's going to tell us, how this particular material is performing. All right, so far we've only really talked about tensile stress, but there are different types of stress, and of course you've had 3401 probably at this point, and you've already sorted these out. But anyway, you need to be able to recognize these. This is tension or tensile stress, so that's a pulling action. Compressive stress, obviously a pushing action, like if you were to close a vise or a hydraulic press down on a workpiece. Now you can also have shear stress. So we'll even talk about shearing in this as a manufacturing process. There's torsional stress, or this twisting action, and then bending or flexural stress. All right, so pause the video here and think about just for a second about where you would see these different types of loading, these different types of stress being applied to this little frame here that's supporting this I-beam. All right, so let's pretend that this is actually a welded steel bar that's hanging here. All right, that bar would be in tension. All right, so that's one place that you would see tension. You'd also see tension up here in this member as it's being pulled on by the downward action out here. Torsion, we would have to introduce another type of force. I don't see any torsion necessarily happening here because all of these pins, we could consider these to be completely frictionless, and this all still works. But if we were to have a slight breeze come through, and I said if this is a welded steel bar, then we would then be putting that bar in torsion. You might see shear here with these pins. So these pins are probably experiencing shear. Where do you see flexure or bending stress? Well, you can see it in the actual weight applied to this bar. It could be bending like that. Also, you see it here because this is this bar is being pulled down here, and it's going to trying to make this this U shape down here. So there's a bending action happening on that bar. And we could even break things down a little further, like we did in Tech 3401. We could see the tension that's happening in the top part of this beam, for instance. All right, but anyway, these should be you should be able to recognize those. All right, so stress is this internally the intensity of those forces acting inside of the cross section of the part. All right, typical units of stress are PSI or really KSI. So KSI, as I'm sure you remember, are kips per square inch, or thousands of pounds per square inch, or also megapascals. So, or you could just talk about pascals, but a pascal is 1 Newton distributed across a square meter. So that's, the way to think about that is, an apple, the force of an apple being distributed across a square meter, which, is a little bigger than a square yard. So that's a very, very tiny amount of stress, and so that's why megapascals are listed here. So PSI and KSI, or megapascals. All right, so stress is generally calculated on the original cross-sectional area of the specimen. So what gives with that? Well, that's a thing called engineering stress, because as we apply, let's think in terms of a tensile test. As we apply a tensile load to a specimen, it's going to stretch out, and what's going to actually happen is its cross-sectional area is going to reduce. But the more conservative way to think about it is to ignore the fact that the cross-sectional area is being reduced, and what that will tell us is how that workpiece or specimen would perform in service under load. All right, we would get a false idea of the strength of that material if we kept measuring the cross-sectional area, because the cross-sectional area, remember, is on the bottom of this equation. It's force per unit area. And as we reduce the cross-sectional area, as the bottom of the fraction gets smaller, then the amount of stress would go up, and we would get a false idea of how strong that material was if we kept remeasuring the cross-sectional area. So just keep in mind what we're using is, in this class, is engineering stress, and we're not, we're going to base that on the original cross-sectional area. All right, this little symbol, I forgot to tell you when we saw it earlier. Let's back up here. That little shape, I think you should already have gotten this from another class, but that is a lowercase sigma. It's like a Greek capital S. All right, so that's going to be our symbol for stress. The symbol for force is, I'm using F here. A lot of times you'll see that as P for perpendicular force, but we're going to just say F, and A for the cross-sectional area. All right, so the reaction of the material to these stresses that come from the loads is going to be deformation. So the material may stretch, it may be compressed, it may buckle, it may bend, but this deformation is a change in form of a body due to stress or thermal change or moisture absorption or any other cause. All right, so even though we're talking about mechanical properties, this could arise from other influences. All right, so this amount of deformation was going to be measured in units of length. All right, so this brings up another question. Remember, we had this little bar bed a minute ago. If I told you that I had a steel wire, and that's welding wire, and it's 30,000ths of an inch in diameter, and I could, with my bare hands, I could stretch that wire an inch. All right, are you gonna take that bet? Okay, and see. So if we just talk about stretching a wire an inch, it leaves a lot of unanswered questions. Okay, let me actually show this little video here. I finally actually broke down and filmed this because I've talked about it, but I haven't actually filmed it until, well, this has been several years ago. All right, so this is me taking a piece of welding wire, and maybe you can see up here in this corner that I put a mark on there, and I'm stretching it with my bare hands, mind you, almost an inch, 2.5 centimeters if you like such things, 25 millimeters or so. But the wire is about 50 feet long. Okay, so the deformation per unit length, the actual deformation, sorry, let me back up. The actual deformation of that wire is about 25 millimeters. But that doesn't tell us anything until we know how long that wire is. So it was about an inch. It was about an inch of deformation, but the wire, as you saw, is about 50 feet long. All right, so let's stop talking about feet and just use the same unit. So that's 1 inch per 600 inches. All right, so 1 out of 600 inches would be the actual amount of strain. So that's 0.00167 or so inches per inch. So at every inch of that wire, I stretched almost 2/1000ths of an inch, which is a much more descriptive way to talk about that. Okay, so what we're talking about when we take the actual length, the amount of deformation that we experienced, and divide by the original length, that gives us this idea of strain. All right, so this is our equation for strain. And if you can really, you don't have to memorize this, you can really arrive at this just by thinking about what's going on. It's the change in length over the original length. All right, well, how do you talk about the change of length? Well, you talk about, you take how long it was when you finished, and you subtract how long it was originally. Okay, so if this thing were originally 600 inches long, and I stretched it 1 inch, then my finished length would have been 601. So 601 inches minus 600 inches would give us 1 inch, divided by the 600 inches of the original length. All of that would give us the amount of strain, which would be a little less than 2/1000ths of an inch per inch. Now, if we had done this in millimeters, all right, then we would have said, well, the original wire was about 15,000 millimeters, which is the same length as the 50 feet, 15,000 millimeters, and we stretch it 25 millimeters, then 25 over the 15,000 is going to give us the exact same number, 0.00167, etc. So a little less than 2/1000ths of a millimeter per millimeter. So the units cancel out. Okay, it's dimensionless, and you will get the same number whether you do strain calculations in feet or yards or furlongs or millimeters or kilometers. It doesn't matter. You'll use what's convenient, obviously. Don't use furlongs. But it will be the same, okay, because the units, inches, divided by inches, cancel out. Now, I'm going to break off and take this opportunity to remind you that if you add inches to inches or add meters to meters, you will get more meters. But if you multiply meters times meters, then you get square meters, which are not the same thing as meters, okay? If you take inches and multiply them by inches, you'll get square inches. You will not get any kind of inch. It is not an inch anymore. It is not a unit of length. It is a unit of area. And if you keep going, if you take area and multiply times a length, then you get volume, a completely different unit. So square inches are not the same thing as cubic inches. You cannot treat them the same way. You can't add them together, things like that. They are not the same unit. I had a dishwasher salesman tell me, or a washing machine salesman tell me one time that one machine was only a half a cubic foot larger, and he said, well, that's just a 6 by 6 inch cube. And I said, no, that's actually 4 6 by 6 inch cubes. Actually, I don't remember if I said that or not. I think I just went with it. All right, but it's a half a cubic foot is not a 6 inch cube, so keep that in mind. You don't just you don't convert cubic inches to you don't convert a cubic foot to a cubic inch by dividing by 12. Okay, you have to do that for each of the 3 units of length. All right, so not to get off the subject, let's start using stress and strain. Now, you should already be familiar with this. If you took Tech 1711, we talked about this stress-strain diagram. We talk about it in 3401 and pretty much any other class, like tool design. We're going to make sure that you see this over and over again because this is a diagram that you really need to have internalized. All right, on this axis, we have stress, and it says engineering stress, and that's what we're typically going to want. Sometimes you'll see a little sigma with a lowercase e under it to talk about engineering stress. And these are kips per square inch, or thousands of pounds per square inch. All right. On this axis, we have strain. And since we're using inches here, we'll talk about this in inches per inch, but it's really unitless. We just sometimes leave the inches per inch there to remind us where these units came from. Also, we'll see a little trick that you can play if you leave those units there in just a little bit. All right, so let's keep in mind how we get one of these. So this could come from a tensile test, for example. We put our test specimen in the tensile tester, and we start stretching that part. We start applying, we start pulling that specimen apart. We start stretching it. So this is the strain axis, and remember, strain is inches per inch. What we would physically see, though, would be the part stretching. All right, so this is the axis where we would see that stretching happening. This is the axis where we see the stress building up. So this we would see on a load cell, and it would be telling us that we were applying a certain amount of force to the specimen, and of course we would have to divide that force by the cross-sectional area. So this is telling us, there would basically be a scale on this side telling us how much stress or how much force was building up, and how that force, of course, we would divide by the area to turn that into stress. All right, so you see very rapidly when we first start pulling on that specimen, the stress builds up quickly. Okay, this section, remember, this is the elastic region. This is elastic deformation. We are not permanently deforming the part at all in this region here. Then we will build up so much stress, then we will see the dial on the force gauge will start to, it will level off. It will stop moving all of a sudden. In fact, it may drop down a little bit. You see the stress can drop down. This is some yield point elongation here. We have an upper yield point and a lower yield point. Some materials will exhibit this yield point elongation in this region here. Not all materials, but some will. And then the stress will start to build up more and more. But look at what we would see. We would see it stretching a lot now. Okay, so very little stretch happens from here to build up this stress. So that means that the dial on the load cell would jump up really quickly. And then it's going to feel like maybe the jaws are slipping or something, because you keep stretching and stretching and stretching, and not much else happens in this region here in terms of stress. But anyway, what will happen is eventually it will reach a peak here. This will be the ultimate tensile stress, and then it will start to drop back down and then fracture. All right, so let's just remind ourselves what these regions are. Remember, this is the elastic region. No permanent deformation happens here. We could build up stress to, say, 30 KSI by stretching it just a little bit, and then remove that load and let it snap back, and it would go all the way back to its original length. That's the elastic region. Then we have the yield point, upper and lower yield point. We see the yield point elongation happening here. And what's happening here is the part is plastically deforming. Okay, so we could be doing something like a forging operation or a bending operation where we're applying enough load to permanently change the shape or length of this material. All right, let's zoom in here on this elastic region and talk about it a little bit more. Okay, so here we have this region kind of exaggerated. We have it tipped over a little bit. And what we see is the slope of this line is what's going to become important to us. Okay, this is the modulus of elasticity. Okay, in this case, since we're doing a tensile test, it's called Young's modulus. So that is the slope of this line, how steep this line is. So, the first way to think about this is to remember how the test is working. Here we're stretching quite a bit and building up stress slowly. If we were to have a stiffer material, then this would be a steeper line, and the stress would build up more rapidly. So the more vertical this line is, the stiffer the material, the higher the modulus of elasticity. So the modulus of elasticity is the slope of this line. It is the rise divided by the run. All right, so how would you find that from a real test? Well, you'd have a series of data points along here, and one thing that you could do is to just take a point out here that's below the yield point, that's below the proportional limit where this line is still a nice straight line, and you could take that and just take its rise, which would be its stress value, and divide by its run, or the strain value at that point. So at this point right here, you see we have a strain value and we have a stress value. We could just divide the stress by the strain. So that would be stress over strain. Let's see, if we had 2 points along here. Now see, this should always start at 0, and so that would be our other point. It would be 0, 0. That assumes that we have nicely calibrated equipment. What you see commonly done in lab equipment is they will take a series of points along here, not just use a single point or 2 points to calculate this slope, but they will actually do a linear regression analysis on this. So they would take and find the best fit of this line, and that's something that you will do in lab, is you'll find the best fit of this line through a process called linear regression that you may or may not have had experience with at this point. All right, so with a high modulus of elasticity, you will get this ability to resist deformation under load. Okay, and if we are in the elastic region, then the modulus of elasticity is the ratio of stress to strain. All right, so a nice linear relationship. And if you know Young's modulus, then you could come up with an equation for that line. Okay, so y equals mx plus b. The e here would be the slope, would be the m in that equation. And if everything calibrated properly, then the b, this y-intercept here, would be 0. So that would allow you to come up with a formula for this line to find strain given stress and given strain. All right, keep in mind that that modulus of elasticity is called Young's modulus if we're talking about tension or compression. There is a very similar analogous property called the modulus of rigidity, and we will use G for this, and that is the exact same concept, only using shear instead of tension or compression. And also, you'll see the flexural modulus talked about in bending applications. All right, so if you hopefully remember more than just this, but if you just think of one thing about E, that is this, okay? This steel bar is the exact same dimension and shape, and it has the exact same load on it as this aluminum bar, okay? The only difference between this piece of steel and this piece of aluminum in this particular setup is E, okay? So this has a higher modulus of elasticity than this aluminum does. It has a more vertical, a steeper slope than the aluminum does. So that's what you need to be thinking of when you see E, is this. All right. All right, so this idea of elasticity, just to beat a dead horse, is the ability for this material to recover from some kind of deformation. Okay, so we apply a load, we remove the load, the material recovers. It snaps back, all right? It can be altered by changing the temperature or by loading it at a different rate, either a slower rate or a faster rate. You'll see a lot of tensile tests will ask you to do the test at a particular rate. Also, there are three different measures of elastic strength, okay? The elastic limit, the proportional limit, and the yield strength. Those all three kind of happen in the same area in certain diagrams. Let me drop down here. Okay, so right here at this spot, we could be talking about the elastic limit. And if we're talking about the elastic limit, then we're talking about physically testing this part, loading it and unloading it until we find a point where if we load it with that much stress, it will not return to its original length. We could be talking about the proportional limit. If we're talking about the proportional limit, then we are talking about this line and where this line ceases to be straight. Okay. Now, all three of these happen at roughly the same point. The last one, the yield point that I haven't mentioned yet, often we'll use this 0.2% offset yield. Okay. The description of the yield point is that what's happened is the material has yielded. That is, we have moved rows of atoms past other rows of atoms. We have physically shifted the atoms in this material. They are no longer in the same place. They have been moved. So that means it has yielded. Now, to talk about the yield point, we could, it's kind of a little ambiguous sometimes when you're dealing with a lot of data points here. So to get a very precise, repeatable value for the yield strength, a lot of times we'll use this 0.2% offset yield. So the 0.2% offset yield is, what we would do is we would find an equation of this line, okay? Or if we want to think of this graphically, is we draw a line parallel to this other line, and we move it over 0.2%. Now remember, this diagram, this axis is unitless, so 0.2% really means 0.2 divided by 100, and just moving over that length. All right, so 0.002 along this axis is where we will place this second line. And where this line, this 0.2% offset line, intersects the stress strain diagram, that value right here on the stress axis is our 0.2% offset yield strength, sometimes called the proof yield. So we talked in 1711 about what's happening inside of plastic, or inside of elastic deformation. That is, we're actually moving or stretching the distance between atoms apart. We're actually feeling, when we move a spring, we're feeling those atoms, that atomic bonding between the atoms, and that's where elastic deformation happens, is between the atoms. But when we start to yield, when we start to deform plastically, then we have slid rows of atoms past other rows of atoms. And one way this can happen is through slip. Okay, so this is this shifting, this dislocating of atoms along these rows or planes. All right, and so this cannot be undone. So once you do plastic deformation, it is permanent. All right, so plasticity is something that we will see in materials that are ductile or malleable. So you'll remember that ductility is the ability of a material to flow under tensile loads, and malleability is the ability of the material to flow under compressive loads. Okay, so a tensile test, we will see ductility. In a compression test, we might see malleability. Okay, so if we see a forging operation, we are seeing malleability. If we're seeing hammering, then it's malleability. All right. Brittleness is what we get when we don't have a good amount of plasticity. If we don't have a material that has much plasticity, we can't deform it plastically, then we will get brittleness. And that's what this looks like. This is a brittle fracture. This is, I think, a piece of cast iron that's been in a tensile test, and it just shears off more or less flat. You see the sides are perfectly straight here. This is a brittle fracture. On the other hand, this is a ductile fracture. You can see that this part has been necked in. Okay, you see the reduction in the cross-sectional area, and you'll also see this what's called a cup and cone fracture. So here, this is making sort of a cone shape on the end of this part of the specimen, and the other side makes a cup shape. So this cup and cone fracture is typical in a ductile material. And also seeing this reduction in cross-sectional area, the good indication of the ductility of a material. Here's just another view of that ductile action. So you see that this was a perfectly straight cylinder when the test began, and as the tensile test ran, it got smaller and necked in like this, and it flowed. The material flowed. And here's another, maybe a better picture of that cup and cone fracture from a nice ductile failure. All right, this is an image of what you would see in a tensile test if you were just looking at the load. Now this says that these are kips, but what's more common, you won't see a load cell that tells you kips. Unless it's a computer system and you have plugged in the cross-sectional area and it's calculating the amount of kips. All right, what you'll typically see is something that says force or pounds or maybe even thousands of pounds or tons or something like that that you're getting your stress numbers from, the load cell that you're getting your stress numbers from. You'll see this dial, and here's what it'll do. The older machines would have a lazy arm on them. And the dial would move around, and it would keep going up and up and up. In fact, what happens is it goes up really rapidly at first, and then it will slow down. You'll see this dial just go slower and slower and slower and slower, and then you'll see this lazy arm stay in position, and the dial will start to drop back down. And then all of a sudden, the material will fracture. Okay, so as soon as you see this dial start to drop back down, you know that fracture is about to occur. And then that point right there on that load cell would indicate where the ultimate tensile strength was. So this would be, if we come back to our stress strain diagram, that would be this point. But when I point here, it's kind of unclear whether I'm talking about a strain position or a stress position. I'm talking about the stress. Okay, so this is what we would get our dial. We would see that dial go up, up, up really rapidly at first. Then it would slow down, and then it would reach a peak, and then the dial would start to drop back down, and then fracture would occur. Okay, so if you just picture what happens in this axis as you move along this axis, just think of the pointer going up, up, up really quickly at first, then slower and slower and slower, and then it will drop back down. Okay, where it reaches its peak on this stress axis, that is the ultimate tensile stress or strength, because we measure the strength in values of stress. All right, so we're almost ready to start using things like this. In fact, you already used this type of formula in 3401, most likely. I talk about it in Tech 1711. The one thing we haven't talked about is the shape. Okay, so to get stiffness from a workpiece or a specimen, there are these things that will be involved. The amount of force that we're applying out here at the end, and this says W for weight, but we just think of that as pounds force, and we could call it P if we wanted to. We could call it F if we wanted to. But we're just applying a load out here at the end. We have the length of that part. And then we have E and we have I. Now, we've talked about force. You already know about length. We just got through talking about E. The only thing we didn't talk about to understand this thing fully is I. And I've put a link in here to our discussion of I in Tech 3401. So that's available there. It's not a video, at least at this point. But there, just to remind you about I comes from the shape. The area moment of inertia comes from the shape. So this is two separate setups with the same formula, the same E, because they're both the same piece of material. But all we do is change I. So we get stiffness from this setup here, and I just want you to understand all of the elements of this. And so I'm going to show you this. All right, so here we have this turned sideways. So that's a lower value of I that we would get. All right, so E is the same in both sides. In fact, I probably should have just played these both at the same time. Look, it bends an awful lot. Okay, if we come over here, we turn this up on end. Now it's in the stiffer position. We put the same load on here, and we can see that it bends much less than it would have if it was turned in this position. All right, so I'll just skip to the end. All right, so we have not changed E here. We haven't changed the length. We haven't changed the load. The difference between this and this is I. All right, so that is the area moment of inertia. We saw earlier the steel and the aluminum where we just changed E. So this is what you need to keep in mind, is this. I will come back and mention, since this is manufacturing processes, look at the huge influence that the length has. Okay, so by having more length out here, this thing will deflect much more, and that's something to keep in mind when we're setting up to do machining and lots of other processes. Is generally we want to keep this short. All right, there's also hardness. So hardness is the ability of a material to resist indentation, and I did this kind of illustration of what you would see during a tensile or during a hardness test. We have a material here. And that material will have all kinds of surface asperities on there and surface roughness and things like that. So in a typical Rockwell hardness test, we'll come in here and we'll apply a little preload first and kind of mash down those asperities. And then the machine will push that ball penetrator or braille penetrator into the material and see how deeply it will penetrate. So a harder material will have, this will be a smaller hole. And of course, this is a grossly enlarged illustration of what happens in a hardness test. Okay, but that's the idea. We're going to try to indent the material, and then we'll, sometimes we measure the actual size of the indentation. So hardness is the ability to resist this. And we'll talk more about that later on. Another couple of things that happen under the stress-strain curve are resilience and toughness. All right. So resilience is this energy that we can get back, okay, out of the process. So this is, let's just deform this spring here, and we're deforming it elastically only. And when we remove the load, you see the energy is conserved. We get the energy back out of the spring. All right, that would be resilience. Now notice here, this is not stress and strain, this is load, and this is elongation. So we have not divided by the cross-sectional area, and we have not divided here by the original length. This is just how much load we applied, and this is how much it stretched. This is the stress-strain curve. Look, it's exactly the same, except here we divided by the cross-sectional area, here we divided by the original length. So it will be the exact same shape, but we'll get different numbers. The area under the elastic portion here, this energy that is conserved, is resilience. And if we take this energy and divide by the volume, then this is the modulus of resilience. Okay, and this is that trick that I was going to tell you about. If you look at the stress-strain diagram, Here we have stress on this axis, that is force per unit area, and here we have length per unit length. If we were to take, so that, remember, stress puts area on the bottom, and over here we have length per unit length. That puts 1 unit of length on the bottom. Sorry, did I say length area underneath? So that means we have length times, let me write it down. Okay, so if we take this is our pounds per square inch, and our stress, and this could be kips, or this could be anything. But anyway, we got pounds per square inch. Down here we have inches per inch. If we multiply those two together, just like this was, if we were trying a length here and a length here, we'd get area. If we multiply these two axes together, then we get pounds over square inches times square inches, or inches over inches. See, if we don't let those units go away, if we don't let them cancel out just yet, then watch what happens. All right, then we get these funny inch pounds. And remember that foot pounds, just like inch pounds, could be a unit of energy, and this is a unit of volume. So this would be, if we look at this area under this curve, then we have energy per unit volume. And that's what you see here done with the pascals. Remember that these negative exponents are per. So meters times meters to the -1 is meters per meters. Same idea. Here you wind up with joules, and here it has times, but this is a negative exponent. So this is joules per cubic meter. So we get this unit of energy per unit volume would be the, basically, if we looked at this as if it was the area under this curve. So that's how we get resilience. That's how we get the modulus of resilience. That's one thing that's happening in terms of the energy. This is the energy that's conserved. There's some more energy. If we look at the total energy under here, the energy that's conserved and the energy that's not conserved during that plastic deformation, then we are looking at a measure of the toughness of the material. All right, so toughness is the ability for a volume of material to absorb a certain amount of energy. Okay, and the way that we measure this is with a toughness test, and we talked about this in 1711, and we'll do more of it in this class. But you put a specimen in a holder, and you whack it with a hammer, and you measure how much energy is expended in whacking that part. The Sharpie and the Izod test are the two most common tests to measure toughness. And we will talk more about those later on. We'll talk about the specifics of those tests later on. But right now we're just understanding what toughness is and why the units are this funny joules, or units of energy per unit volume. All right, you can also have dynamic loading. That is a loading and unloading. And one way to test the fatigue strength of a material is through a rotating beam test like this. So what's happening here is these are ball bearings. So here we have a spindle that's mounted in bearings, and out here we have a workpiece that's mounted in that spindle. On the end of that workpiece we have another ball bearing, and we apply a load on that bearing. Then as we spin this, you see, if we picture this not spinning, first of all, then the top part of this is in tension, and underneath here it's in compression. So if we rotate this, then the part that was in tension will then 180 degrees later be in compression, and vice versa. So this is a way to apply tension and compression back and forth very rapidly, and you can get millions of cycles without too much time. So you can load and unload, tension and compression over and over again in this rotating beam type test. And a couple of numbers that we could get would be the fatigue strength. That is the maximum stress that we could apply without ever causing failure, and the endurance limit, and that is the maximum stress below which a material will not fail regardless of the number of cycles. Okay, so let me show you this on this graph here. All right, if you had a piece of steel, if you stay below this amount of stress, okay, this about 30 KSI, if you stay under here, then you could load this piece of steel back and forth with, say, 25 KSI for the foreseeable future. Okay, so notice this is a log scale down here, So this is 1,000,000 cycles by the time you get to here. So it could just go on and on and on and never fail. Aluminum, on the other hand, does not show this nice clear endurance limit. Okay, and so it doesn't matter how slight the load is, eventually aluminum is going to fail. All right, so there's this difference in endurance limits, and aluminum does not have it. All right, so we said we talked a little bit about failure at the beginning. There are types of failure. The definition of that failure is the change in the characteristic that makes it unsatisfactory for use. We talked a little bit about slippage, and the slip is a mode of plastic deformation. Another one is twinning, but I'm not in this class. I'm not going to talk too much about that, if at all. But slip and twinning are two of the most common modes of plastic deformation. Creep is plastic deformation that happens slowly. Okay, so you may have a part hanging from a material that is susceptible to creep, and it may hang there for several days and not be damaged at all. In fact, it might be well below the ultimate strength of that material, and yet you come back a few days later and you see that the part has stretched out. Okay, so that slow action is creep. Let's say we've seen some separation, some cleavage, some fracture. This is when the part is going to actually, the end of the tensile test, when the thing comes apart. Of course, cleavage is that fracture along different planes. And we can also see buckling, and you're going to see this in like a compressive test where the part fails in a compressive manner. All right, so that's our introduction to mechanical properties, and hopefully you saw most of this as a review, and we will start moving forward next time.